Birzeit, and in particular Wafa Khater, played a crucial role in the local organization of the school that year. So this year, we hope to have a school that's different in many ways. It's bigger. This year, we're planning to have around spontaneous CP violations in to understand. I see. Yeah, the AC it's called. So Hans Storer is an outstanding researcher in particle and nuclear physics, and the topic that he will talk about relates to the origin of matter-antimatter asymmetry in the universe, and how one can learn something about that from laboratory experiments, from extremely precise experiments. Hans is one of the very few people in the world, I don't know really of any other, but I haven't searched very deeply, who won 2 ERC grants, advanced ERC grants, back to back. So these grants are for the really top of the researchers in Europe, and winning one of them is typically not something everyone does. Winning 2 of them, yeah, I don't know how to do that, but I'm going to ask Hans and see if he can tell me the answer. We're also going to hear a special lecture by Imad Barghouti, who some of you might know very well. He's a professor at Al-Quds University and an expert in theoretical space plasma physics. So Imad will talk about science in Palestine and also about his... Now, I should say that we're particularly grateful to our host this year, to Birzeit University. Organizing a school like this, in particular from the outside, as we are, the international organizers are all located in Europe and in the US, it's quite hard, actually. There are many things that have to fall into place. This is true for anything you organize, any sort of conference, that there are many aspects, many administrative details that needs actually to work. But it is particularly hard to organize it in a place like Palestine. And then it's critical that you have local partners that are both trustworthy, reliable, and really do what they say they are going to do. And we're extremely happy to have identified in Birzeit such a partner. Birzeit has a long and recognized tradition of working with international partners. So there's a course here run by the ICTP successfully for many years. And we're extremely happy to be here at Birzeit. And this in particular as the scope of the school and or the location of the school was changed in last minute. So there were many details that had to be figured out on a very short timescale. So the local organizers of this school include Dr. Ismail Badram, who will say a few words in a minute, Dr. Wafa Khater, who also did great work last year in organizing the school. And then, in particular, we have had great help from what we call the Operative Local Organizing Committee. These are Rula Bakir, Nida Al-Badr, and Sameh Othman. If you would stand up, if you could. And yeah. Let's give them a clap right away, because they've already done outstanding work, and they will continue to do outstanding work because, as I will describe in a bit, they'll be responsible for some things that you will contact them about. There's also an international organizing committee who worked on this school over the past year. This includes Nabil Iqbal, who's standing in the doorway, Madalena Lemos at DESI in Hamburg, and Leo Bannon at the University of Southampton. Me, I'm David Mars, I'm at Cambridge, and Mario Martone, who's sitting there from University of Cincinnati, and also Kate Shaw from the ICTP. We've also had great advice from some quite senior researchers in physics. This includes Philip Argyris, Professor Michael Berry, Professor John Ellis, and Professor Stephen Hawking. This school wouldn't be possible unless we had funds to bring in the lecturers and fund housing and everything that comes with it. And this year we've received funding to a great part by the crowd in a so-called crowdfunding campaign. This crowd consists of 201 backers who generously responded to our crowdfunding call that we put up on the Fiat Physica webpage. We asked to raise $7,500 US for this school. They responded by raising us $15,383. So there are 201 backers of this call. They've given anything from $1 US to 1,000. Here's a list of a few of them. The full list is available on the Fiat Physica webpage. They come from all over the world, and I think it's fair to say that all of them are really interested in you having a good time here. So please feel supported by all these people. Moreover, I would like to in particular recognize the importance and the contribution by Stephen Hawking. So Stephen, we discussed our crowdfunding campaign with Stephen, and he decided that he wanted to support it on his Facebook page. So he put up a notice on his Facebook page saying that I was pleased to send a greeting to the Palestinian master students attending the first Palestinian Advanced Physics school last year. The school was greatly appreciated by both the students and the lecturers. I support the rights of scientists everywhere to freedom of movement, publication, and collaboration. In this spirit, I would like to bring up a fundraising project aimed at raising funds to make a second Palestinian Advanced Physics school possible. Please consider making a donation today to support science in Palestine. Signed, Stephen Hawking. So Stephen has, I don't know, maybe it's around 3-4 million followers. So when he wrote that message, our fundraising site, Fiat Physica, got completely bombarded by people interested in funding science in Palestine, which made that their servers crashed. It took them a few hours to set it up. They did great work in responding so quickly to the challenge. But Stephen's, the contribution of Stephen in publicizing this fundraising campaign cannot be underestimated. We also received some funds from the International Center for Theoretical Physics, ICTP. They have been very generous to us. And we'll discuss ICTP and their activities more in subsequent days. They offer some opportunities for students from Palestine and elsewhere. So with those introductory words, I would like to give the word to Dr. Ismail Badran from Birzeit University.
Thanks. I would like to thank you all for coming to Birzeit and welcome. We knew on Birzeit this was supposed to be happens in Al-Quds University, not Birzeit. For the last month, we switched to Birzeit. Welcome and thanks for the organizing committee. Thanks for the lectures and thanks for the students. And you are welcome here.
Okay. Thank you very much, Ismail. So now there's some practical information that we would like to relay to you. The first of these is to register. I see name badges on basically everyone in here, which is an indication that you've already registered. Those who haven't should go and find their name badge. Maybe find a schedule, a notepad, and your name badge. Your name badge is important because it's the key to get lunch tickets. Without lunch tickets, we can't provide you with any lunch. So please hold on to your name badge. The operative local organizing committee, so Rula, Nida, and Same, are the ones who will each day distribute lunch tickets to those who still have their name badge. Please see them when they ask you to collect your lunch tickets. For those of you who require dorms, the operative local organizing committee are again the people to see. The way this will be organized is that at the end of the day today, you will go and see them, and they will lead you to the dorms that you will be using. There will be 2 social dinners during the school. The first one is tomorrow evening, and the second one is on Wednesday evening. In both cases, we meet at 6 p.m. On Monday, we'll go to a restaurant, and on Wednesday, we'll go to the observatory to have a lighter evening meal. We will distribute, or the operative local organizing committee will distribute forms to fill out during the lunch break with meal preferences that you should fill out. Now, there are certificates to be earned, if you would care to. To get a certificate of attendance, you would need to solve problem sets and hand in those problem sets. So without handing in problem sets, no certificates. Also without being registered, no certificates. So we will hand these out at the closing ceremony on Thursday. Phones off in the lecture hall, it goes without saying, but it's easy to forget. So please be considerate and turn them off. The website for this school is hosted by the Indico service at CERN. You can find it under this address, or just Google the Palestinian Advanced Physics School 2017, and this will be a top hit. It includes a timetable, and it will include lecture notes, and also the problem sets will go up here. So it will be an important page to check. We would also strongly encourage you to follow Scientists for Palestine's Facebook page. That would include some photos. It will include some photos, some information about the school. Please share the posts, and if you want, post on the page and contribute to make this event visible, so that perhaps students elsewhere would even more like to go next year. there's already a streaming going on, a video streaming. So Birzeit University is streaming these lectures and this opening on their YouTube channel. And Facebook, there's a Facebook live stream that's available from the Scientists for Palestine webpage. So this will mean that, well, people from all over the world might also follow the lectures that you will be hearing. Okay, so there are two contact information numbers in case of emergency, in case of that you need some practical information to the members of the Operative Local Organizing Committees, Osama and Rula. They're up here. These lecture notes will go on the Indico webpage, so if you can find that, you can find the numbers, you can get in touch with Rula and Sama. Okay, without further ado, let's get started. So the first lecture that we have is David Tong, who will be lecturing about condensed matter physics. So let's give him a great hand.
On. Excellent. Very good. Can you hear me now? Good. How are you all? Good. Good. Firstly, I should say everybody's been saying thank you to everybody, so I should just add my thanks. Thank you to the organizers for inviting me. It's a real honor and a pleasure to be here, and I'm very much looking forward to this week. I tend to speak really fast. Is this an okay? Can people understand my English, at least? My English is so-so, but people can understand? Okay, very good. I'm going to tell you about something called condensed matter physics. Who here knows what condensed matter physics is? No one has ever heard of condensed matter physics. Two people. Okay, let me tell you firstly what condensed matter physics is about. It's actually one of the biggest topics in all of physics. And the goal is very easy. The goal is to understand what stuff does, where stuff can be anything at all. So the goal is just to understand how things work, how materials work, and it starts with very, very basic questions, the kind of questions that a child would ask. Things like, why is water wet? Or why are metals shiny? Or why is rubber bendy and stretchy? Because they're all made of exactly the same atoms, and yet they have these very, very different properties. And so the goal of condensed matter physics, to begin with, is just to try and understand this. Why does stuff have the properties that it has, and how do you distinguish between different kinds of matter, different kinds of stuff, and how do we understand where that comes from? And it starts with very, very childish questions, but very quickly it becomes much, much more interesting, and we start to ask questions about quantum mechanics that underlies the atoms. And we start to discover new materials that arise that have very surprising features, things like superconductors, or things like quantum Hall effect, or more recently graphene or topological insulators. So there's this continual excitement in the field where new materials are discovered, and we understand how these work. So that's the essence of it. I should say it used to be called solid-state physics. Who's ever heard of solid-state physics? All right, good. Now it makes sense. So there was a change in advertising in the community, I think in the 1970s, because everybody who wasn't a solid-state physicist thought solid-state physics was really boring. And so the people who were solid-state physicists decided they should change the name. So they changed it to condensed matter physics, in part because what they were interested in were things that weren't solids. It was things like liquids, which obviously isn't a solid, but more and more interesting materials that came up. So that's what we're going to be doing. What used to be called solid-state physics and is now called condensed matter physics. I should check. Who's done a course in solid-state physics? Okay, so I'm not quite sure how to balance these lectures. So I've got one lecture to give now, but if everybody knows this stuff already, we can change. So I'm going to talk about something called band structure. Who knows what band structure is? Okay, so about two of you. You're all going to be really bored, those that put your hands up. For the rest of you, it's something beautiful, so hopefully we can learn something. Let me tell you one thing. There's some lecture notes which I've written for this school. They're quite long. They're about 60 pages long, and they contain many more details than what we're going to do here in the lectures. But it'll be useful to download them. They're on the website. They will be on the website of the conference very soon. And all the details of the calculations, some of which I'll do in lectures, some of which I won't, but all the details are there. So if you really want to learn the subject, as always, it's best to sit down and just go through these calculations properly. But everything is in these lecture notes. All right. I'll stress a little bit about the philosophy of condensed matter physics, because it's very different from other areas of physics, and in particular it's very different from particle physics. Because in particle physics, and I should say that I sort of grew up as a particle physicist or someone that was interested in fundamental aspects of the universe. And as a particle physicist, the question you want to ask is, what are the basic constituents of matter? So we know that there are quarks and electrons and W bosons and very recently the Higgs boson, but what we're interested in is what lies underneath that. What's the fundamental constituents? Is it supersymmetry? Is it string theory? I mean, we don't know, but we hope to find out. In condensed matter physics, it's completely the other way around, because we know exactly what the basic building blocks of stuff is, because it's atoms. And so there's no mystery about where everything comes from. In fact, there's a sense in which there is just one equation in all of condensed matter physics. So let me tell you the equation, which is, if you're a condensed matter physicist, this is the theory of everything. This explains everything you could ever possibly want to know. And it's this. All right, let me explain this. Do we have a pointer?
Yes, that's one.
I have my finger, but do we have a different pointer? Does this work?
Yeah. Let me give it to me.
Okay. All right, so what?
Middle.
Brilliant, good. So what's going on here? We know that everything's made of atoms, but when they're inside materials, what often happens, so the atoms, of course, have a nucleus with electrons going around them. And what often happens inside materials is that electron gets stripped away, or some of the electrons get stripped away. And so what you have in materials are electrons that are free to move around, and then what are called ions, which is a nucleus with some electrons, but not enough electrons to cancel that positive charge. So it's a charged ion and electrons. And all of condensed matter physics, which is to say every single thing you know about in the universe, can be explained in terms of electrons and ions interacting. And it can be explained with the following formula. So what is this? This is a Hamiltonian. So we're going to do quantum mechanics here. And it's a Hamiltonian that describes a bunch of electrons interacting with a bunch of ions. Okay? And there's 5 terms. So what are these terms? The first one is the kinetic energy for electrons. Okay? So little m is the mass of the electron, and little p is the momentum of the electron. And the kinetic energy is p squared over 2m. And if you have a whole bunch of electrons, I don't know if you can... Shall I make my slide bigger? Can you see this letter here at the back? No, it's an N with a subscript E, a capital N with a subscript E. And N subscript E is just the number of electrons that we have in our system. Okay? And then there's a whole bunch of ions, and each of those ions has a momentum, which I've called capital P, and a mass, which I've called capital M, but the masses of the ions are not necessarily all the same. So there's an index here, alpha, which labels which ion we're talking about, and the number of ions I've called N subscript I. Okay? So a bunch of electrons, a bunch of ions, and then they interact with each other. And the way they interact is through the Coulomb force. They just feel this electrostatic attraction or repulsion. The charge of the electron is... So that's it. So if you want to know anything in the universe, all you have to do is just go and solve this equation. Okay, it's that simple. And notice there's a lot of fantastic things in physics that we just don't care about. There's no special relativity that's needed. There's no general relativity that's needed. Orbiting usually a proton, but you can take it to have any charge that you like. So then we can solve it. Of course, that's when we can solve it with pen and paper. But if we want to do better, we can just put this on a computer. And we can solve it on a computer. So we get to solve this on a computer if you have, I think, something around 20 ions and 20 electrons. That's something we can do on a computer. But of trying to solve this, we have to be more creative, of thinking about what's happening in materials and just choosing different starting points to understand what's going on. So a large part of condensed matter physics is that level of creativity of thinking that we can't start with the fundamental building blocks. We have to assume some things and then write down new equations and then try to solve those. So that's part of what we'll be seeing in these lectures is how we proceed with this. Okay. By the way, I was told that you never ask questions in lectures. Is that right? Is it? Has anyone ever asked a question in a lecture who's here? Yeah? Yeah? Do you want to ask questions? It's going to be so much more fun if you ask questions. Okay, good. Any questions? Too simple. But do just shout out. Any questions, just ask. It'll be brilliant. But then it slows things down. Yeah, you should just shout out, and I'll repeat the question if people care. So please, do feel free to ask questions at any time. Okay. Are things clear so far? Very good. All right.
Don't worry.
All good?
Yes. I will do it.
Let me say one more thing. I told you that for the fundamental laws of physics for condensed matter, you don't need to know special relativity, you don't need to know general relativity, you don't need to know quantum field theory. One of the lovely stories is that as you proceed and you understand condensed matter physics, all of those other theories feed in some way. And never in the obvious way. They always feed in a rather surprising way. So it turns out to really make progress in condensed matter physics, you actually need to know all of those things. So from my perspective, it's one of the lovely things about this subject is how it fits in very unexpected ways with particle physics, with gravity, with special relativity, and with various other topics. To give you one example, the theory for a superconductor, the mathematical equation, is exactly the same as the mathematical equation for the Higgs boson, which strikes me as a shocking fact, but it's just true. So somehow if nature has one good idea, she likes to use it in many, many different places. Very same equation arises in different parts of physics. All right. So in this lecture, I'm going to tell you about a topic called band structure. Let me explain what band structure is. Okay, so it is a fact that when you look at the vast majority of materials, of solids in particular, you find that the atoms within the solid are arranged in a regular periodic fashion that we call a lattice. Okay? Many, many different types of lattices can arise, but nonetheless all these solids have this property that they repeat themselves over and over again with the atoms stuck in very special positions. This already is a non-trivial fact. It's a fact that you can try to prove from the previous equation. It follows from the previous equation, but it turns out to be very, very hard to actually prove it rigorously starting from the previous equation. So for the purposes of this lecture, we're not going to prove it, we're just going to take that as a statement about how solids act, that they have this periodic structure to them. So here is an example of a lattice. Okay? And so we have this solid lattice that's regular. And then we're going to ask the following question. There's an electron, and we want to ask, how does an electron move through this solid? Okay? Very straightforward question. So if I have a solid and I throw an electron inside it, what's the electron going to do? That's the topic that we're going to address in this lecture. And, as a physicist, if someone asked me this and I didn't know anything, this is what I would think. I would start thinking classically, and I would start thinking that this electron is something like, you know, a little ball, some kind of marble, or, you know, some round object. And if I throw it, then it's got all these things in the way, all of these atoms that are stuck in the way. And so I might think, well, you know, I might get lucky. I might be able to throw it at exactly the right direction so it goes through the gaps in the lattice. But that's going to be very lucky, and most times I throw it, it's more likely just to bounce off one of those atoms and then bounce in some other direction and bounce in some other direction. So in my head I would have this picture, my first guess, would be that if I throw an electron in a solid, what it does is it bounces around like this. Okay? Maybe it gets stuck. Maybe it gets stuck in some region and just bounces around. Maybe it doesn't quite get stuck. Maybe it drifts slowly in some direction. But this would be my naive intuition for what an electron would do if I was to throw it inside a solid. Does everybody agree with me that this is likely? For the classical view, great. So the wonderful story is this is not what the electron does at all. Okay? The electron is not classical, as you say. The electron is a quantum particle, and when you throw it inside a solid, what happens is it barely even notices that the lattice is there. Okay? The lattice does have some effects, but not many. But what the electron really does is just glide beautifully through this lattice without changing direction, without losing any speed. It just continues, like I said, almost as if the lattice isn't there. With some small effects, and those small effects are what's called band structure, and that's what I'll explain in this lecture. Okay? I should add, it's crucial that the solid is regular and periodic. If it was just random atoms in random places, then that classical viewpoint of things moving around and getting stuck is exactly what does happen in the quantum world as well. So there's a story called Impurities and Disorder, where if you don't have a regular periodic lattice, things do get stuck. But with a periodic lattice, when you throw something, it just moves through unimpeded. Okay, so what I'm going to do is firstly tell you the punchline, and then this lecture will be going through the equations to convince you that this punchline is actually correct. Okay, so to get to the punchline, suppose the lattice wasn't there. If the lattice wasn't there, you would throw an electron in empty space, and its energy is given by something that we learn in school. It's the kinetic energy for a particle, which is a half times mass times velocity squared. Okay? And then as we get a little more sophisticated, we rewrite this in various ways. So the first thing we do is we introduce momentum. Momentum is mass times velocity, and we rewrite the energy not as a half mv squared, but as p squared over 2m. And then when we get to the quantum world, we write momentum as h bar times something that's called the wave number, or the wave vector, and then we write the kinetic energy again as h bar squared k squared over 2m. So it's this form that we're going to use in these lectures. Okay? And we can plot it. Of course, it looks like a quadratic. So this is a plot of the energy versus the momentum. Do you know, we're lazy in physics. So k should be called the wave vector, but all physicists actually just call it the momentum. And it's not the momentum. They differ by h bar, but all physicists just say k is the momentum. Because by the time you're talking about this, you basically never use p. You only ever use k. So I'm going to refer to k lazily as the momentum. And this is my attempt to draw a quadratic equation on PowerPoint. So this is what the energy versus the momentum looks like. Okay? And what I want to tell you in this lecture is that if you put a lattice in the way, so this electron is moving inside a material, then this changes and it becomes this. So what happens here? It takes roughly the same shape as it did before. It's still basically quadratic. But the big surprise is that there are these gaps. And so there's certain values of the energy that the electron can never take. As you increase the momentum, the energy gets bigger and bigger and bigger. And then as you increase it one bit past a little point, what happens is the energy jumps by some discrete amount. Okay? So this is the essence of what's called band structure. This is called the band. It's the width of energy which is allowed. So this is one band, this is another band, this is another band, and what's in between here are called band gaps. And so the purpose of this lecture is to try and convince you that this is what happens if electrons move in solids. Okay? Again, just to get some idea, who's seen this before? So, okay, exactly the same people who had said they'd seen band structure. Very good. Just checking for consistency. Good. Okay. For those who haven't seen it before, is it clear what I claim I'm going to show? Has anyone got a question? Let me ask it that way. This is with the lattice. Great. So without the lattice, just half mv squared. And with the lattice, you get the gaps appearing in the spectrum. Okay. Other questions? Yes, please.
This is what caused this gap, that the electron units will be the same as the energy levels in the atom. So the atom absorb electron or not?
Yeah, that's not what's happening here. Yeah, so we're actually not taking that effect into account. So what's happening is we've sort of forgotten about what the particular atoms are, and what's happening is that when the electron has this particular momentum, it's bouncing off the lattice a lot. And so this should become clearer as we go on, but for most momenta, the electron just washes over and doesn't see the lattice at all. But for very specific momenta that is related to the spacing of the lattice basically bounces the electron backwards and forwards, and that's why these gaps appear. So it's to do with scattering off the lattice, but scattering that can only happen when the electron has very special values of the momentum. Okay, that's where we're going in this lecture. Other questions? Okay, good. But by the way, in this lecture I'm just going to show you this, and in the next lecture I'm going to show you why this is important. But for now we're just going to understand why the gaps appear. Okay, so we're going to do, the plan is to do the following. It's to write down two toy models. So these are two very simple equations that are supposed to capture the physics, and then we'll solve those equations and we'll see that this kind of physics is what emerges. And we're going to do two toy models where the starting point is very different, but nonetheless the end point is roughly the same. So the first toy model is called the tight binding approximation, and the second toy model is called the nearly free electron approximation. So I'm going to explain to you what these models are, what the starting point is, and then we're actually going to go through and solve them. I should warn you that the solving them is a little bit fiddly, and so I will do everything on the board or on the PowerPoint. Whether or not we'll be able to follow in real time, I'm not sure. I think it's probably a bit too much for one lecture. In particular, this took me 3 lectures to get through when I taught students in Cambridge University. So to try and do it in one lecture is maybe asking too much. But I'll try and give you a sense of what the calculations are. And like I said, all the details are in the lecture notes that are online. Okay. All right. So this is our first model. It's called the tight binding model. And it's a rather extreme model of what happens in a solid. So what we're going to think is the following. Firstly, I'm only going to consider a one-dimensional solid, just because it's easier. All of this we can do in higher dimensions, and I think in a later lecture I may do this in one higher dimension. But for now we'll just have a one-dimensional solid. So it's an array of atoms, and the atoms have a distance between them, and that distance is little a. Okay, so there's one atom, distance a, another atom, distance a, hello. So, okay. So the slightly weird thing about this model is we won't allow the electron to move anywhere in space. Okay, instead we're going to say that the electron is stuck to one of the atoms, and if it wants to move, it moves by a quantum jump to the next atom. Okay, so the electron can only sit on the places where the atoms are. So that means that the electron states are discrete. One here, one here, one here. That's the only places it can fit. All right. Okay, so what we're going to do is the following. The electron is going to move on this lattice. It might sit here, it might sit here, it might sit here, and so on. This is going to be quantum mechanics. So I'm going to introduce a state in the Hilbert space for every position where the electron can sit. So what I'm going to say is that if it sits on the nth atom, this I guess is n equals 4, starting from here, 1, 2, 3, 4. If it sits on the nth atom, the state of the electron I'm going to call this quantum state n. So n goes from 1 to the total number of, little n goes from 1 to the total number of atoms. Okay. And what I'm going to do is take the total number of atoms. This is annoying to say. The total number of atoms is also going to be n, but it's going to be capital N. So little n goes from 1 to capital N, where capital N is the total number of atoms, and therefore the total number of places the electron can sit. All right. If it sits here, it's completely orthogonal in a quantum sense to if it sits here. So what I mean by that is that the overlap between a state on the nth atom and a state on the mth atom is the delta function delta nm. So it's either 1 if they sit on the same atom or 0 if they sit differently. Okay. Finally, just to make things easy, and you don't have to do this, you can solve it in other ways, I'm going to make the whole thing periodic. So I'm going to pretend that these atoms are arranged on a circle, and the way I'm going to do that is by saying when I go to n plus 1th state, that's the same as going back to the first atom. Okay, so that's what this equation here says. I've imposed some periodicity where when I get far enough along here, I just come back round to this point. Nabil, I'm running out of batteries. Can you... I can use my finger in the meantime. Okay, are there any questions about the setup, about what we're doing? Electron sits on discrete atom sites. Yeah, please. No, so the distance A is going to come later when we solve for the states. But for now, just think in your mind they're A apart. But it's not playing any role in the Hilbert space. The Hilbert space is the same regardless of the distance A. Does that answer the question? Great. Thank you, Nabil. Other questions? Okay, so this is the setup. And to explain the dynamics, I need to tell you the Hamiltonian, because as always in quantum mechanics, it's the Hamiltonian that tells you how things move. So I'm going to pick the following Hamiltonian. So let me firstly just walk you through it, and then I'll tell you why this choice of Hamiltonian is a sensible thing. So the Hamiltonian is, of course, an operator on the Hilbert space, which means that I give it a state, and it spits out another state. It moves the particle either one to the left or one to the right. Yes. Okay? Except, remember, this is quantum mechanics. And so particles don't have to be in a particular place. They can be in both places at the same time. So what that second term actually does is take a particle that's sitting at one point, it's at E0, and it splits it either side with a probability associated to the hopping parameter t. So this particle takes a state where this Hamiltonian takes a state, the particle is quite happy in one position, and what it does is it splits it into a superposition of 3. Okay. And so that's what this second equation here is trying to tell us. If we think about the time-dependent Schrodinger equation, that's the one that has d psi by dt equals h psi. It tells us how things change in time. And so this equation here is that equation for a very short time interval, delta t. And so for every short time interval, what's happening is this Hamiltonian is taking the particle that's in one place and splitting it into 3. And then the next time, it'll take each of those places and split it into 3 again, and then into 3 again. Okay? So it's a rather, it's a very simple Hamiltonian, but it does this rather complicated thing to the particle where it's making it constantly move apart, so it's now in a super. Is that because this is so easy, or is that because this is so hard? I can't tell. Yeah. Okay, so what we're going to do is the following. We're going to solve the quantum mechanics with this Hamiltonian. Okay? If the quantum mechanics was just the first term, it would be very easy. What does it mean to solve the quantum mechanics? It means you solve the Schrodinger equation h psi what the eigenstate. Okay. Okay. Are there any questions? Or diagonalizing an n by n matrix, which is a linear superposition of these localized states, and the coefficient here is a complex number, psi subscript m, and the mod squared of psi m tells you the probability that you sit on the given site m. Okay? So this is the general state that we can write down in quantum mechanics. And so what we do is we take this general state and we plug it into this equation and we act on it with this Hamiltonian. Okay? If you do that, this equation here becomes this equation here. Okay? So this is an equation, quantum state plus some other quantum states equals new quantum state. And what we can do now is take it from an equation not of quantum states, but just an equation of numbers. And we do that by taking this object, n, and hitting it on the left of this equation. So if we take the overlap with n, what we end up with are a bunch of linear equations, simultaneous equations that we have to solve. So these coefficients psi n have to obey the following equation. So this equation here is just the same as this equation here with this Hamiltonian. Okay, any questions about this? You know, it's the kind of thing that's best done in the privacy of your own homes rather than on stage in front of people. But it's sort of standard quantum techniques of just going through the algebra to understand, to get the final equation. All right, so this is just to recap what we did on the previous slide. You take a general state and you expand it in the following way. And when you plug it into the Hamiltonian Schrodinger equation, you have this equation here. Okay. Now these kind of equations crop up again and again in physics. It's exactly the same kind of equation that you get if you get a bunch of springs and you couple them next to each other and you want to solve normal modes of springs. Exactly the same equation. And the way you solve it is very straightforward. Well, I'm not sure this is the way you solve it. The solution is the following. Psi n is an exponential. Okay? So psi n is an exponential e to the I. K is any number that you like times na. If I plug this in to this, you can prove that it solves this. Actually, I was told to set problems. This strikes me as an excellent one. Take this, plug it into here, prove that it solves it, where E is some particular function of K. So for every K, you'll get a solution, but the energy here will depend on K. Okay? I'll write this down and the organizers will give it to you. But show that this is a solution to this. Okay. All right, so we went through some details and it gets a little bit messy, but that's the essence. You get to solve the Hamiltonian for this type binding problem. This is the solution, but this is something you've seen before. Because if you didn't have atoms or hopping or any of this, if you just had a particle that could move on a line, then the solution to the Schrodinger equation is a wave function that we call a plane wave, and it's a wave function which is e to the ikx. Okay? This is exactly the same. In particular, remember what's going on here. The subscript n tells you which atom you're on. n equals 1 is here, n equals 2 is here, n equals 3 is here, and so on. And the distance between them is a distance a. So the distance na is, or the number na is precisely the same as the distance x along the line. Okay, so this na here is completely analogous to this here. The difference is that x can be anything usually, and in our model, you are only allowed to be in very special places, so the value na is something that's discrete. N is an integer, whereas x can be any real number. Okay? But it's the first hint that lattices don't do very much different in quantum mechanics. We started with this model where the thing can only be in discrete places, and the eigenstates that you get out are very, very similar to the eigenstates of just a particle moving along a line where it can be anything at all without things in the way. Okay, so it's the first hint that we see that in quantum mechanics, particles can just move through lattices almost as if they're not there. All right. There are some differences, though. So the difference really is in the fact that this NA is an integer multiple of A, whereas X is anything. In particular, that means that if I take this wave function and change this number K, so this number K is, in this kind of wave function, K is related to the momentum in this way. You know that because the momentum operator is minus I h bar d by dx. And if you act, it brings down h bar k as something here. So the momentum is related to k, so we're going to call this k here the momentum as well. And the novelty in the lattice model is that because this is an integer, if I shift k by 2 pi divided by a, these numbers don't change, because e to the 2 pi I is the same thing as 1. So what happens in the lattice model is, the only real difference is a little bit surprising. It's that the momentum can't be anything if the particle is on a lattice. So if the particle is on a line, the momentum can be anything at all. If the particle can hop on a lattice, it can't have any momentum. The momentum sits within some range, and we choose that range. We could have chosen that range to be 0 to 2 pi over a, but we actually decide to choose that range to be symmetric between k and minus k. So the range that the momentum can take is pi over a, minus pi over a to pi over a. So there's only a finite amount of momentum you can have if you're on a lattice. Okay? Minus k is going that way, positive k is going that way. So that's the big difference that the lattice has, is that the momentum can't be anything, it can't be arbitrarily large, it has to be in this finite range. Okay? We give this range a very fancy name. It's a name which I am unable to pronounce, I'll tell you now. I can tell you the English way of pronouncing it. The English way of pronouncing it is brillouin. And the French way, you have to cough a lot more when you say it. So brillouin, something like this. Okay, so there's a French guy called Brillouin, and it's his zone. He's the person that... actually, he's not the person that first understood this. The person that first understood this is a brilliant physicist called Rudolf Peierls. But it's always the case in physics that the people that first understand things are very rarely the people that get their names on those things. So this is a good example. This should be called the Peierls zone, but it's called the Brillouin zone. All right. Any questions about this? Yes, please. No, so here I didn't put in any of that information, and the Brillouin zone, the range that K can take, completely independent of the type of atoms, and in this particular model, everything is independent of the type of atoms.
So it is equal between the atoms have equal A, equal K?
Yeah, so A is just the distance between the atoms, and that's all that matters in this model. In the next model we look at, we'll put in a bit more detail, and we'll see that the type of atom is going to change something. But for now, in this simple model, only the distance between the atoms matters. Yeah, good. Other questions? Okay, so let me give you the summary of this first model. By the way, this is the answer to the homework problem. It's worth writing this down. Remember, the homework problem was to take that solution and plug it into the equation, show it solves it, but to find out what the energy is. So if you do that, this, it turns out, is the energy of the state that has momentum k. And I've plotted it here. So k only goes between minus pi over a and pi over a. This is in units where a is equal to 1. So if you can just see, this is minus 3.141, blah, blah, blah. And if you plot the energy spectrum, it looks like this. Okay. So there's a few things to take away from this. The first is what I said before. You might think that the electrons want to be stuck on one atom, or maybe just spread out over a few atoms. And that's not what happens. The electrons want to move along the atoms almost as if the atoms weren't there. So the energy eigenstates are just electrons that have some fixed momentum k in one direction or another. Okay, that's the first lesson. The next lesson is that the electrons can't have any energy that they like. They can't have arbitrarily large energy in this model. The energy just lies within one particular band. And as we saw on the last slide, that's because they can't have arbitrarily high momentum. Their momentum is fixed to be within this, this range, this Brillouin zone. So bits look very different from what we're used to in the absence of a lattice, but some bits look very similar. And in particular, suppose we think about a particle which has very small momentum, so moves very slowly. So if k is small, I get to Taylor expand this when k is small. Now for k small, cos k is the same as 1 minus a half k squared, plus k to the 4 terms that we can neglect. So if I Taylor expand this energy, then the energy that you get is a constant piece, which we just don't care about, plus something which goes as k squared, and then there'll be higher terms that go as k to the 4 and so on. But this term here, which is the only bit that depends on the momentum, is exactly the same form as the energy, the kinetic energy that we learn about in high school. It's the same half mv squared, where we replace, as before, v with momentum and the momentum with k. So the energy of a free particle is h bar squared k squared over 2m. I'll call it m star. And to match with this, the effective mass that this particle has is given by the following. It's given by h bar squared over 2t a squared. Okay? So what's the way to think about this? If the particle's traveling very slowly, then it has a very large de Broglie wavelength. Okay? And with a large de Broglie wavelength, much bigger than the lattice spacing, it basically just doesn't see the lattice at all. So when the particle moves very slowly, it's got a big wavelength, it glides over the lattice as if the lattice wasn't there, and that's why its energy looks exactly the same as a particle in free space. Okay? The slightly surprising thing is that the particle picks up a mass. We didn't give the particle a mass in our model. There was no way mass came in, but it picks up a mass, and the mass is given by, well, h bar squared, because it's a quantum effect, and it depends on from one atom to another. So it's a very counterintuitive way of thinking about mass, but nonetheless, for very low momentum particles, they can't tell the lattice is there. By the way, here's an interesting problem to do. How do we know that our world, space, is continuous? You know, we always work with space being continuous, but how do we know if we don't go down to tiny, tiny distance scales, much smaller than we've ever explored, we wouldn't find some lattice structure there where we actually have to sit on a very particular lattice point? And the answer is we don't. We don't know this at all. So you could ask the following question. Suppose that our world was like this. We know that for very low momentum, we wouldn't be able to tell the difference. That's what we're seeing here. How high would the momentum have to be? Well, let me say it differently. For a fixed lattice size, which presumably is very, very tiny, maybe Planck scale, how high would the momentum have to be before you would detect the difference from our world? Meaning, how high would it have to be until this kind of bends over and you see something different? It's worth playing with some numbers and just getting a sense for that. Was there a question? No question. Okay. Okay, any questions? Good. Yeah, please.
For this study, when we got the Hamiltonian.
Yes.
So I just want to have one question. The states, the definition of the states are orthonormal.
The states on different lattice sites were orthonormal.
Yes,
That's right.
So the toy model told us even though the states are orthonormal, the superposition probability is still more than one state at the same time because we put the Hamiltonian. We operate the Hamiltonian.
Yes, exactly.
Even though the states are orthonormal.
Yeah, but no, it's the same as in normal quantum mechanics. So in normal quantum mechanics, the state where a particle is localized at this position it's a little bit fiddly, much more so than this, because it's a delta function at this position. And the delta function at this position is orthogonal to a delta function at a different position. And yet, nonetheless, we think about wave functions spread over all positions. So it's really completely analogous to the usual case. All right. Let me tell you one more thing about this particular model, just because it's going to be important for the next lecture. We could ask, how many states are there here? Because at the moment, it looks as if k can take any value. But that's not quite true. Not only does k have to be restricted to this range, minus pi over a to pi over a, it actually only takes very specific discrete values within that range. And those discrete values come because of the periodic nature of the lattice. So remember I said right at the beginning that when I go to state n plus 1, I want that to be the same as going round to state 1. That means that I want to impose this requirement on my wave function, that the bit of the wave function at n plus 1 is equal to the bit at 1. If I plug that in, I get the following requirement, and this only holds if k takes values that are integers times 2 pi divided by a times the number of atoms. So the momentum has to be in this range, but it's in little, very tiny, discrete increments within that range. And so you can ask, how many states are there in total? And, well, this is the range that the momentum takes from here to here. But rather than being continuous, it actually just takes discrete values given by this. So I divide this range by this. And what I find is that I get exactly n different quantum states. But it had to be n quantum states because that's how many I started with. And I can't grow quantum states or lose quantum states. All I can do is just rearrange them in some other linear superposition. Okay? So it's a general statement that's going to be important, but in every Brillouin zone, the number of states is equal to the number of atoms that you have. Here we did it in this one-dimensional example, but it's true for any solid. There's something called a Brillouin zone. It's a region in finite momentum space, and the number of states is equal to the number of atoms in the solid. Okay. All right, that's the end of the tight binding model. And now we're going to look at something, a very different way of looking at lattices. So any questions about the tight binding model before we go on? All happy? Okay. All right, let me tell you another way to think about lattices. And this is called the nearly free electron model. And we're going to forget about the tight binding completely. This is going to be much more similar to the kind of picture that we usually have. The electron isn't going to be restricted to be at particular lattice sites. The electron can move quite happily backwards and forwards along the line. However, it's going to experience these atoms because it will feel some kind of potential. So if there's an atom here, there'll be a big potential, usually attractive because the ion is positive and the electron is negative. But for the purposes of this model, it can be anything you like. So the potential does something here. And then there's nothing, and then the potential does something here, and then there's nothing, and the potential does something here, and so on. And you ask the question, how do you know what kind of atom it is? Well, this is where you get to put in the information. It's in which potential the electron feels as it gets close to that atom. Okay. So I'm going to consider the following Hamiltonian. It's an electron that can move backwards and forward on a line. We're still going to be in one dimension. And it has the usual kinetic term, half mv squared, or momentum squared over 2m, plus a potential term. And the potential can be anything you like as long as it repeats. So the potential at this point has to be the same as the potential shifted over here, where the distance is again going to be a. Okay? With the understanding that we're trying to model a bunch of atoms that are separated by a distance a, and the whole thing is regular. Okay? That's the only assumption. So here's one example of a potential. Here's another example of a potential. It really doesn't matter for any of this as long as the potential repeats every distance a. That's all we need. Okay? All right. I'm going to do one more thing. To make contact with what I did before, I'm going to put this particle on a circle. So it's going to come back to itself after some distance. The size of the circle is going to be L, but now there's a requirement, because when I come back round, the potential has to kind of match onto itself. So this requirement is that L divided by A is some integer. And that integer is capital N, and you should think again of capital N as the number of atoms which are on this circle. Okay? Any questions about this? Yes, please.
So the potential term in the Hamiltonian, it comes from the atoms.
Yes.
So can the potential be the delta function?
It can, and in fact, I think for the delta function, there's an exact solution for this. So we're actually going to solve using perturbation theory, but there's some very special potentials where you can write down an exact solution, and delta functions are one of them. It's got a name. I think it's called the Kronig-Penney model. If you want to Google, what's that? But Bloch's theorem. Bloch's theorem is a general theorem that holds for. Yeah, Bloch's theorem holds in general for this kind of Hamiltonian. Yeah, I won't actually do Bloch's theorem in these lectures, but it's obviously an important part of the whole story. Yeah, it's in the lecture notes if you want to look in more detail. Other questions? Okay, so this is the new Hamiltonian that we want to solve. And the way we're going to do it is we're going to use perturbation theory. So what's perturbation theory? Perturbation theory is where you have one part of the Hamiltonian that you just know how to solve because you've seen it a billion times before, and another part of the Hamiltonian that's new, and as long as the new bit is small compared to the first bit, you get to sort of start with a good approximate solution for the first bit, and then perturbation theory tells you how you correct that solution to get the proper solution. Okay. So what are we going to do? We're going to take, as the bit we've understood before, just the free particle, and we're going to think about the potential as a perturbation on the behavior of a free particle. Okay? And we can worry about when it's valid and when it won't, and I won't actually worry in this lecture, but you can make it all much more rigorous than I will. All right, so what do we do? What we do is we start by thinking about the eigenstates when the potential vanishes. So the eigenstates just for the free electron. And we know very well what these are. In fact, we even saw them just 4 slides back. The eigenstates are things that are plane waves that carry momentum k, and I'm going to call them these states here, and their wave functions is given by, the e to the ikx, and I've normalized the wave functions by dividing by 1 over the square root of L, where L was the distance around the circle. Okay? And the energy, of course, is just the energy that we've seen several times. It's a half mv squared, but now written in terms of this wave vector. Okay. So if there's no potential, it's very straightforward. We just get these plane waves. Again, these plane waves are orthogonal. This is orthogonal now with a Dirac delta function, but this is a formula that we'll need on the next slide. Okay, so what do? We want to do perturbation theory with this potential V. But if you remember perturbation theory, there's 2 different kinds of perturbation theory. There's degenerate perturbation theory and non-degenerate perturbation theory. And the whole thing is horrible, I'll grant you up front. The way it usually works, at least in my university, if you do non-degenerate perturbation theory, we always make people calculate it to second order, and if you do degenerate perturbation theory, we always make people calculate it to first order because it's really, really horrible at second order. Does that resonate with you all? So it turns out that here all these issues arise, and it's actually rather subtle. The interesting point happens when degenerate perturbation theory is interesting. So remember, degenerate perturbation theory happens when you have 2 states which have exactly the same energy, and when you act with a perturbation, they kind of mix between them. Okay? And here, there's always 2 states with the same energy, because the particle can go that way with momentum k, or it can go that way with momentum k. Okay? Plus k and minus k, in other words. They have exactly the same energy because the energy goes as k squared. And if you think about it, that's exactly what you might expect the lattice to do, is to mix those. Because with a lattice there, you might think that the particle going that way bounces off and goes that way. And if it keeps the same energy, then it has to go plus k to minus k. So that's actually the key bit of physics in how the lattice affects a particle moving, is that it can make it bounce off. And so what we're going to do is do degenerate perturbation theory with two states, one with plus k and one with minus k, and just see how the lattice mixes these two states. And we're going to find that the real energy eigenstate isn't something going that way or something going that way. It's actually something going both ways at the same time, because this is quantum mechanics and it's cool, and particles can just do interesting things like that. All right, I should warn you that this is by far the most technical part of the lecture. I'll try to go through, but in honesty, it's probably too much to do in one lecture. But let's see if we can do it. So, got a lot of equations. Can you see this at the back? Is it legible? Not really. No. Okay. I'll not down the front either. Okay. I'll try and write bigger next time. Let me tell you the essence of what's going on here. This is something I'm going to claim, and this is the proof. So the claim is the following. It's that when the momentum takes very special values, and only when the momentum takes those values, the lattice can send something moving in that direction to moving in that direction. But only for very special values of the momentum is this something that can happen. And those special values are when k is equal to pi over a times an integer. Now, that's something we've seen before. In the tight binding model, pi over a was the maximum momentum that the particle can have. Okay? In this model, the particle can have any momentum at all, but when it takes very special values of the momentum, that's when the lattice can take it going from one direction and make it move in the other direction. Okay? So that's the claim. When the momentum takes these values, the potential scatters a state plus k to a state minus k. And the proof is basically just lots and lots of tedious Fourier transforms. So this is basically what's going on. I'm going to take two states, k and k prime, and k prime is going to be the state minus k. And when you do perturbation theory, the thing you want to look at is the matrix element, which is one state, the perturbed part of the Hamiltonian with the other state. In other words, you want to look at k, v, k prime. And the important point is that, and this is where we need the fact the potential is periodic. This is only true because the potential is periodic. But because the potential has this periodicity, you can Fourier transform it, and it only has very specific Fourier modes when you Fourier transform it. So it has these modes whose frequency goes as 2 pi I over a times some integer. And these coefficients, you can do the inverse Fourier transform to write them down. So the essence of this is the following. It's really the fact that this only takes certain Fourier modes, and then when I take this matrix interval, I only get a non-zero answer for very special values of the momentum. Okay? And I'm not going to go through the details, but that's the essence. Certain periodicity means that only certain momenta get scattered back off. All right. And the momenta that you need are precisely these ones. Okay, so what do we do with this? The potential can only scatter particles that have a very particular momenta, integer values of pi over a. And so when the particles have that very specific momenta, you need to do degenerate perturbation theory, which means the new eigenstates are going to be some linear combination of things going that way and things going that way, where the coefficients I'm going to call alpha and beta. This is the calculation of degenerate perturbation theory. Again, there's sort of a standard procedure you can go through. It's just a 2x2 matrix. You figure out its eigenvalues. The eigenvalues turn out to be given by the following. So how should I understand this? This is the energy, a half mv squared. H bar squared, k squared over 2m, but where k is taking this very special value. So this is the energy that these particles had before there was any lattice put in. And what's happening here is these energies get split, and they get split by an amount that depends on the value of the potential, but what's really happening is the correct eigenvalues is that way plus that way, and that way minus that way. So these are the new energy eigenstates, and the energy isn't continuous there, it gets split. So if you go through this calculation, what you find is what I promised at the beginning of the lecture, that the energy of the particle with momentum k very roughly follows the quadratic that we had before, the k squared quadratic, except whenever this lattice can bounce the particle off the other way, the energy gets split. And so you have these gaps in the energy where, well, there's no quantum state that has energy inside these gaps. This is going to be very important for the next lecture. The gaps happen at these very particular values of pi over a. The first we've already met, that's called the first Brillouin zone. And then the region between pi over a and 2 pi over a is called the second Brillouin zone. And then the next region is called the third Brillouin zone, and so on and so on. And inside each Brillouin zone, the number of states turns out to be exactly the number of atoms, capital N. Okay? So comparing with the type binding model, the type binding model just gave us this. And that's really because we only allowed a finite number of states. But this model, the free electron model, or nearly free electron model, the momentum can be anything, but there are these gaps that appear in the energy spectrum. All right. Any questions about this? Please.
When we prove that k equals n pi over a,
Yeah.
we assume that the lattice is Fourier transform. Is every lattice a Fourier transform? Can we transform it?
Yes, as long as the lattice is periodic.
As long as
Yeah, then it has a Fourier transform.
So there are lattices are not Fourier transform.
If you have to search for some very weird functions for that. So if it's on a finite, if it's periodic because it's on a finite circle, and it's got some periodicity a, guaranteed that it can, and it's smooth basically, or continuous, then guaranteed it can be Fourier transformed. Yeah. Other questions? Okay, so these are the two facts you need to take from this lecture. If you didn't follow calculations, it's the following. The energy spectrum of a particle when it moves in a lattice has gaps, like this. And the gaps appear at very special values of the momentum. In this case, the momentum is pi over a and minus pi over a, which we call the Brillouin zone, and then extra multiples of that. And although we did this just for a one-dimensional lattice, it turns out both of these facts continue to be true for arbitrary lattices in arbitrary dimensions. Okay? As long as you have a periodic structure in your lattice, this is what happens. So let me try and just give you some examples without doing the mathematical details before we go. By the way, if you want all the mathematical details, they're all there in the extra lecture notes. So one particular thing you could imagine, here's the next simplest generalization. Take a square lattice in 2 dimensions. Okay? So the particle now moves, but it experiences atoms that are on some square lattice. Then what you find is exactly the same. The particle, in fact, it's really just 2 copies of what we did, because it's going in the x direction or going in the y direction. But the momentum of the particle in the x or the y direction has jumps in the energy at these very special values of kx is pi over a, or ky is pi over a. So this is a plot now, not of the actual spatial lattice, but of momentum space in 2 dimensions. So this is the momentum in the x direction, this is the momentum in the y direction, and this is the origin. And as you go in the x direction, what you find is that this is the edge of the first Brillouin zone, and there will be a jump in the energy. And this is the second edge of the second Brillouin zone, and there will be a jump in the energy, and so on. And the same happens in the y direction. But what's interesting is what happens if you move in neither the x or the y direction, but just at some angle. And these are where the edges of the Brillouin zone are. So as you go along, there's always a jump in energy, and here it's color-coded. So as you go in this way, when you hit the edge of this yellow square, there's a big jump in energy. And then again, when you hit the edge of the pink triangle, there's a big jump in energy. And when you hit the edge of the blue triangle, there's a big jump in energy. So these are the edges of the Brillouin zones. And as you go along and you increase your momentum, the energy jumps with some finite amount. Okay? This is the essence of band structure. Let me try and show you something from the real world. So this is what I'll finish with. So most materials in our world, not all, but most are three-dimensional. And it turns out there's many, many different kinds of lattices that you can have in 3 dimensions. They're not just cubes, but lots of really interesting, funky shapes. Only 3 of them actually appear in most materials. It's rather surprising. The ones that appear are the cubic lattice. That's just things, atoms arranged on the corners of a cube. But other lattices, one called body-centered cubic and one called face-centered cubic. So a body-centered cubic lattice has atoms on the edge of a cube and another one in the middle. And the face-centered cubic has atoms on the edge of a cube and then a bunch others that sit on the face. And for each of these lattices, there's what's called a Brillouin zone in momentum space. So the Brillouin zone in momentum space is, as you go in different directions, it's the point where the energy is going to jump. And the Brillouin zones are complicated. So if people have looked at lattices, I'll tell you the words. There's something called a Wigner-Seitz cell, and the Brillouin zone is the Wigner-Seitz cell of the reciprocal lattice in momentum space. What that means is there's a bunch of mathematical tricks you can do to calculate where this Brillouin zone looks like in momentum space, and they're very complicated. So for a BCC lattice, this is now a picture in momentum space. So this is when you're sitting still. Coming this way is moving in the x direction. Going into the board is moving in the y direction, and this is moving in the z direction. And what's drawn here is some complicated 3-dimensional solid, which is the edge of the Brillouin zone in 3 dimensions. So it's really very complicated. And what people who care about these things do, the experimenters and the theorists, is they try to understand what the energy of an electron moving in this lattice looks like. And so these plots are very confusing, I should warn you. So what are we doing here? You want to know if the electron is moving in some 3-dimensional space, what its energy is. And of course, to do that, you want a function of the 3 different momenta, kx, ky, and kz. And it's very hard to plot a function of 3 momenta because you need 4 dimensions to do it. So you want energy as a function of those 4 momenta. So what they do is, I think it's terrible notation, but these guys probably know better than me. What you do is the following. You take this Brillouin zone, which is the 3-dimensional thing in momentum space, and you look at very special points in the Brillouin zone, and then you draw lines from one point to that point to that point to that point, and then you draw the energy spectrum as you move around on those lines. So if you look in textbooks, you can see lots of pictures like this. So let me do some examples. Every single area in all of physics needs something called the origin. And every single area in all of physics calls the origin O, because that's the sensible thing to call it. If you work in crystallography, you don't do that. You call the origin the gamma point. So if you ever see gamma associated to one of these pictures, that's this thing here. Gamma means what energy does a particle have if it's sitting still. Okay? Why they call it gamma, I don't know, but they do. So this is the momentum when you sit in the middle of this, i.e. sitting still, and these are the different energies that a particle can have. And then as you move in some direction, delta is one of these faces. As you move towards one of these faces, the particle gets faster and faster, and you can see its energy increases. And its energy increases like k squared. It looks very similar to a free electron. But then at some point, you can start to see there are these gaps. These gaps are exactly the same as the gaps in energy that I showed you on the previous transparency. Okay, so this is all to say it gets very complicated in real materials, but the essence isn't so hard. The essence is all there in the example of a one-dimensional lattice. The particle can't take any energy at all. It can only take special energies with gaps. And in the next lecture, we'll see why that's so important. That's really the basis for all these materials, is the gaps in the energy that the particle can have. All right, I'll stop there and see you tomorrow. I'm happy to answer questions if there are any.
Is there any? We have 5 more minutes for questions.
Yeah, please.
So it says it doesn't depend on what type of atoms you find.
Yeah.
If I change the particle charge, what particle I'm dealing with, or if I activate it, does that change what I'm dealing with?
It would change some of the details. So if I go to this tight binding model, oops, this doesn't work. So I put a potential in here, okay? And as I went through this horrible, tedious calculation, the potential turns into these numbers Vn. These are the Fourier coefficients of the potential, but they basically tell you how big the potential is. And these Vn appeared here, which by the time I get to this picture is telling you the size of these gaps. So what's happening is the following. The place where the gaps appear, that's the value of the momentum, that depends only on the spacing of the atoms. Okay? But the size of the gaps, that depends on the details of the system, which could be what charge the atom is, what type the atom is, what charge the electron has, and so on. So the size of the gaps depends on that, but the existence of the gaps doesn't. And nor does the position of the gaps. They always appear at exactly the same place. That depends only on the distances between the atoms. Does that answer your question? Other questions? Yeah, please.
So the limitations of the momentum for that free electron model, it's like it has limitation or discrete values. I mean, for the brilliant zone, it is the maximum value. I mean, the surfaces are the maximum values, or there's more space for the momentum.
Good. So there's two issues here. The first is that I put this whole system on a circle, and that means momentum can only have some discrete values, but they're very small. So this looks continuous, but actually there's a discreteness here. It can only come in intervals of 2 pi over a times capital N, but capital N is the number of atoms in the system, 10 to the 23 or something. So there's that issue. But then the other issue is, can the momentum be bigger than just this first Brillouin zone? And in the nearly free electron model, it can. The momentum can roughly be anything you like. Yeah. Was that the question? Or did I misunderstand? Yeah.
هذا بحب يسأل بالعربي أو خليط عربي وإنجليزي أنا بترجم يعني بساعد في الترجمة فما تخجلوا مهم المعرفة. I was just telling them if they want to ask in like another language,
yeah,
Arabic
please.
or a mixture, Arabic and English, I could help
Perfect.
in translation.
How stable is this calculation with the existence of impurities?
Say that again?
How stable is this calculation with the existence of impurities?
It doesn't work at all. You can add impurities. In fact, there's something rather nice. If you add impurities, if you had just say one impurity, you get one extra quantum state, and it sits in here. It sits inside the gap. And so what happens is as you start to add more and more impurities, right, so yeah, two things happen. Firstly, you start to fill in the gaps, but secondly, the existence of momenta itself stops working. So it's not something I mentioned, but momentum follows because you have translational symmetry in a system. That's Noether's theorem. And here you only have discrete translational symmetry, so Noether's theorem doesn't hold, but there's something called Bloch's theorem that takes its place. And as soon as you no longer have discrete translational symmetry, you don't have Bloch's theorem either. And so even labeling things in terms of momentum becomes not a good idea. There's no such quantum number. But if you just have one, you can get away with it, but you start filling in the gaps. Yeah. All right, more tomorrow.
Okay, can you hear me? Yes, of course. Maybe it's better like this. Okay, so we have lunch is going to start in about 15 minutes. So we're getting lunch here today. You don't need your tickets for today's lunch. So those tickets are for the cafeteria from tomorrow onwards. But we have 50 about the problem solving sessions. Okay. I think as a participation to the school, you need two things. You need to be a registered student, which I think most of you are, and we need to work on sets that will be assigned. Okay, so each of the 3 lectures will write some problems. You know, David already stated one, but we'll have it printed from tomorrow. We'll work on it, and if you work on all the problems, whether or not you solve them perfectly, you get a certificate. Okay? So the way in which the problem solving sessions are going to work is that we're going to split in 7 different groups. Each group will work with one of us, meaning either me, David, Nabil, one of the 3 organizers, or one of the 4 speakers, Hans, David, Anne, and Giorgio, who is on his way. So we have 7 organizers and speakers and 7 groups. We'll form the groups and we'll work each day for about an hour starting from tomorrow on trying to work on the problems, and you can ask questions about the lectures, how to solve the problems, and it will be smaller groups, so much more involvement. Is it clear? Good. So the way we're going to form the groups is by, basically, you're not going to be with your best friends, unfortunately. Right? Because the idea is that we want you guys to be, talking to other, your best friends are already your best friends, the people that you talk physics, you're already talking physics with. We want you to talk to people which you haven't talked physics with. Okay? So how are we going to do split you apart so that you are not going to be with your best friends? I'll tell you in a second. So we have 7 groups. So group number 1 will be with Ann Nelson. Group number 2 will be with Hans. Group number 3 will be with David Tong. Group number 4 will be with Giorgio, who hasn't arrived yet, but he has crossed the border, so he's on his way in a taxi. Group number 5 will be with Nabil. Group number 6 will be with David Marsh. And group number 7 will be with Mario, with me. Hey Giorgio. Yeah, so here's Giorgio. He just arrived. Great. Okay? So those are the 7 groups. Can you read it? More or less? 1 with Anne, 2 with Hans, 3 with David Tong, Giorgio, 5 with Nabil, 6 with David Marsh, 7 with Mario. Okay? Now, starting from the back, we're going to go one by one, and you'll tell a number. We'll start from 1, then 2, then 3, up to 7. Right? You will be in the group of the number that you say aloud. Okay, so the person next to you, which is probably you be your closest friend, is not going to be in your group that way. If the person that is 8 seats next to you, then it's going to be in your group, but not the person next to you. Okay? So can we start from the back in saying aloud a number? 1 and then... So Hans is not counting, so then you. No, 3. Sorry about that. 3. 7. Okay, so each one of you will be in different groups. Is it good? Remember the number that you said. Then start from here. 4. 4? then
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 4. 1.
You were at 6? 7. You guys are remembering the number you said? Because that's the group you're being part of. Okay? Five. Sorry. 4, 5. 7. No, you're 7? You're 7. 1, 2. Okay? So, can we split? I want to see the first group. So, can we all come out next over here? The first group, and can you stand up and get next to N and just say, introduce yourself and each other. Then the second group goes next to Hans. Hans, can you raise your hand? If you said 2, go to Hans. If you said 3, go to David Tong. If you said 4, go to Giorgio. If you said 5, go to David Marsh. Oh, to Nabil, sorry. 6, David Marsh, and 7 to me. So just introduce yourself, and then we'll go to lunch. Okay. So if you said number 2, you are with Hans. Group 5 is different. Nabil. Group number 5 outside Nabil. Group number 7. There must be 2 more people. 7. 7. Number 7. Number 7. Number 6.